So we want to look at how you can do that summing, and then what things are important to know in series. That's the purpose of this. So because they are series in nature, so if we're going to have something like some sum, and then you determine where it starts from. If you want, it starts from 0 to infinite. That is, if you want. If you don't want, take it to infinite. It can start from even 1, but because you're dealing with infinite series, that would be the nature. Then you want to understand what is happening on the right. So such ones, these will be easy. But the ones that are nice is where they don't give you that something, and then they ask you to find a something. And that's an interesting one. So let's go straight now to what is important in this. When you're given a series, you need to know how to find it. That's the thing. You need to know how to find the sum of the series. And then to get a sum of the series, for example, if I have this as my sum as a series again, and then this is the formula, let's say to get the partial sum of this, you say I will just get the limit. Whatever number I get here, this number is going to be the sum of the series. And then the most nice thing to be talked about here, maybe it's a geometric series. Geometric series. This is the name of type. So I have. I don't get the problem was thing is 100%. Okay, I should be audible enough now. Assuming so. Okay, so we went to bring in the issue of the geometric series now, and that is a series of this form, which has the sum n running from 1 equals to the infinite of a r n minus 1. Which is a plus ar squared plus ar3 plus, so it goes on like that. So this is the geometric series where but this one is very much applicable in most cases. You will see when we go to the Taylor sheet how it pops in, and then how we appreciate it in most cases. This one I was just mentioning it. Now on the same geometric series, we have got several properties. That one, if a is 0, this series will converge. It will converge to 0. The geometric series. So if a is 0, then the series will converge to 0. And now you're wondering what kind of a series is going to be if a is 0. It has to be something like a constant. that is 0 also. And then, or if R is less than 1, if the absolute value of R is less than 1, meaning that if -1 is less than R, which is less than 1, then we'll say this converges to it converges to A over 1 minus R, like that. And then if the third case, if R is greater than 1, or maybe even you allow it to be equal to greater or equal to 1, at the same time A is greater than 0, then this is going to diverge to infinity. And then the fourth case is if R is greater than or equal to 1 and A is less than 0, then this is going to diverge to negative infinity, like that. And then the last one is that if R is less or equal to -1 and A is non-zero, then it will diverge. Well, the only thing we know is that to diverge, we won't know whether it is divergent to the negative infinity or positive. We just say it diverges without knowing the actual thing. Okay. That's a good one. I think the nice example should come from the system. But for now, we just pick it that since we may not have that term, let me pick an example that illustrates some of these here. An example like if you have a sum, if I have a sum, n is running from 1 to positive infinity of 1 over 2 to the power n minus 1. Okay. So it means that in this case, our A is 1 because A is always the coefficient of what is powered. As we can see here, A is not any power, but R is one that has the power. So A is 1 in this case, and then R is positive half. Okay, so then how do we get to check if this series converges or not? So now here we use the formula, which we didn't apply. We're supposed to write it actually. Which comes as a limit. So it will come as a limit as n goes to infinity of this guy, which is given by A over 1 minus R. So where the sum is this one here, let's have everything. Here. It's the SN. So in this case, because I've already known what our A is 1. And then we have our R is half. So you work out this. So you work out this and get 2. Like that. So every time I'm given, I just check the power and then I check if it looks like a geometric series, then I know I have to get the limit for me to understand if there's convergence or divergence here. And if I'm able to get the limit as a number, then I know this converges to that number. Okay, as you've said here, that it will always be that limit that you want to check. Okay. What else here? We have several types of series. Several types of series that are there, like the telescopic series, where you always look at what you're given. So in this case, so I'll just say this is our second series. If you have a series of the form n running from 1 to positive infinity of 1 over n, and then n plus 1. So if I find step of a series, I know it's a telescopic series. And then, well, if you are to pick just the sum, just the inside thing, you write it alone. You notice that if you break into partial fractions, you have a over n, you have e over n plus 1. So this, after you resolve into partial, you get that one to be 1, and then the other one to be minus 1, and then n plus 1, like that. So that when you're looking for the partial sums of it, it becomes easy for us to conclude that, okay, so if I have this case, then it means that that I'm able to pluck out the partial form, the limit of this whole thing as n equals to infinity of this Sn to be 1, which is telling us that there is convergence to 1. So every time I see this format here, then I know that, oh, okay, so this converges to 1 because I'm able to get the sum in that manner. Well, it will be expanded for you sometimes, sometimes not. You may just find the right-hand side of this where they do the expansion, and then they can ask you to find the general term. But the good part with series is that you can never find an open series. Every series, then they'll put some general form of it as you go on. So you find that the last term that they indicate is a general form of that series. So you just get that one and then put it under the sum. Like in the Taylor sheet where they're putting, yes, in the Taylor sheet, for example, question 4A. Question 4A of the Taylor sheet, they're saying, identify the series which converge from the following series, find the formula for the nth partial sum, and use it to find its sum. So we have 2 plus 2 over 3 plus 2 over 9 plus 2 over 27 plus they are now giving us a formula 2 over 3 to the power n minus 1. So this is able to retrieve all the other terms. For example, when n is 1, we get 2 over 3 to the power 0, which is just 2. Okay. So if they're saying find the sum, then you just pick this one and bring it here. 2 over 3 n minus 1. Your job is to identify where it's starting from. So it should start from 1 so that you're able to get the first term here. Because when n is 1, I have 1 minus 1, which is 0. 3 plus 0 is 1. Then 2 over 1, that is 2. When n is 2, we have 2 minus 1 down, which is 1. So 3 to the power 1, so 2 over 3. When n is 3, this will be 3 squared, which is 9. So you're able to retrieve all the other terms from there. Then now you use it to find the partial sums. So how do I get the partial sum? You do the limit as n equals to infinity of 2 over 3 n minus 1 and check what you're getting. Okay. So for some questions, if you want, if you still remember the thing, then maybe you not remember the exponential graphs of these, they can also give you an idea of what you get to. But the thing is that for as long as I'm going to infinity and I have the variable in the denominator here, then this will brush off to 0. And that has to be the sum of whatever I'm getting when I push them to be together. They should vanish because it can't blow off to infinity in that case. Then we also have the harmonic series. So we also have the harmonic series. We're calling it 3. The harmonic series 1 over n, where n is starting from 1 goes to infinity. Well, this should be 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. It keeps going like that. And this one, because of this guy, with its special character, let's say, if you look at the Sn, which is 1 plus 1 over 2 plus 1 over 3 plus 1 over n. That's how I was saying this last thing here is the one that you always take in the sum if they ask you to give the sum. As you can see, once you write the Sn, you always have that thing as the last thing in your series. Okay, so this one comes from a deep study of the Riemann sums that we don't go in depth here, where you understand it that, okay, I'm just getting the sum of areas of rectangles where you're looking for the area under maybe some function that will make 1 over x. From you break down your x, and then you're forming the triangles. And well, though we haven't done that I use, but here you understand that the most appreciated one is just to get, since you're talking of the areas, you get the integral of this 1 over x. The x I've changed to x so that I can differentiate because I'm using n as the limit. And then also the 1 over x that will give us the ln of x. Get the x, and then you have limits from 1 to that. Substitute the limits, you get the ln of n plus 1 minus ln 1, which is 0. So if you get the limit as n equals to infinity, this, you understand that for sure this has to be. So you're saying that, so every time I have a harmonic series, I understand that there should be derivatives reaching to infinity. Harmonic. Well, then now we have serious properties now that you look out for, because you may not manage to be solving every series that you are given. So you need some tools to be using. The first one comes as a theorem. What does it say? Well, it's telling us that if you are given a series in terms of its sums to positive infinite, and you have an which converges. So if this converges, then the limit as n goes to infinity of an should be equal to 0. So if you're given such kind of a series and you identify that it converges, well, then you know that if you pick the sum and then get the limit as n goes to infinity, it should be equal to 0. You understand how we're using the sum there? And this one is very open, no much conditions on the end. Just want it to run from one to the other. Then another one, the second version says, well, as n goes to infinity of an, this guy is going to converge if and only if, a very serious condition, if I have this sum that runs from the capital M to infinity of an converges where n is greater or equal to 1. So this is like forcing itself to be some kind of a comparison test, but don't necessarily the comparison test. So where you're saying, okay, if I have this sum that is too big, from n is equal to 1 runs up to infinity. Well, this is going to converge if and only if I'm able to pick some number n that is bigger than that 1. So it means that you have lifted the starting point. Okay. For some reasons, you don't want to start from 1. Maybe you want to start from 10 to infinity, and then you're able to tell that this converges. Well, if this converges, then you are sure that even if you went back and did everything starting from 1 to infinity, this should be convergent. For as long as this converges, this should be convergent. And for as long as this converges, also, if I have this convergent, it will imply that I can lift the starting point that is too big. A bit of some nice things there. Okay, then let's see. There's an example that is applying those two concepts there. The first one is asking us to find the sum of series find the sum of series n is 1 to infinity, and then 1 plus 2 to the power n plus 1, everything over 3 to the power n. So how do you do that? So because of the plus that is there on top there, what we'll do also is we'll split them. So first get 1 over 3 power n. And then this is n equal to 1 infinity. That. But this, we can write it as we want to write it as a geometric series. I put 1 there to infinity. So this is the same thing as 3 to the power negative 3 to the power negative n if I want. But then Because if you remember the geometric series, it needs the power to be n minus 1. So it means for that case, we're not lifting it. We'll write it as 1/3. And then, because we know 1 to the power n is still 1, so we can put an n here. But we want it to be n minus 1. So what do? Well, we work out the 1/3. And then 1/3. The remaining one now is n minus 1, because I know this is to the power 1. Same basis, if I add the powers, I'll get back to my n. So the 1/3 constant can always come out of the sum, and then we remain with 1/3 to the power n minus 1, which is purely geometric now, whose a is 1/3. So now I want to get the limit as n equals to infinity of the sum here, which is a over 1 minus r. So in this case, a is 1/3, and then 1 minus 1/3, the r. So you should be able to work out this and get 1/2. So that was just for the first piece, because we had to separate these as the sum as n equals to 1 to infinity of 1/3 power n plus 2n plus 1/3 power n. And then you split the sum because it's a sum. So now what about the second one? The second piece as n equals to 1 to infinity 2n plus 1/3n. So this one you say, okay, first I will reduce the other one to 2 so that we get 2n/3n, which you can write as 2/3n like that. Then again, we want to force it to the geometric series. So how do we force it to the geometric series? Well, this 2 is outside. Then we get the 2/3 here evaluated, and then the remaining 2/3 now is going to be raised as n minus 1, because if we add, we get that. So now these 2 outside, can multiply the 2 inside there, so that this becomes the sum, of course, from 1 to infinity, and then that would be 4/3, and then 2/3 n minus 1. Like that. So that's how it's going to be. Then now we get the limit. So say the limit as n goes to infinity of Sn is 4/3 as our a over 1 minus 2/3. So you work out this, should be able to get 4. Like that. So now, because we're adding these 2, so you add this plus 4 for us to get the sum of the original series there. So you say the sum of that original series is going to be half plus 4. So you add half plus 4, should be able to get 9/2. Okay, so let's see if we can have a session again in the night. We look at the convergence tests for positive series. Now we have the integral, the comparison, the limit comparison. Series a bit of them. So we did that thing already. We can comment there. And then if you have any questions on the arc length and the like, you can ask them that time. Okay. So enjoy the rest of the day.